This week's lecture, we are concerning about how to implement those pipeline mechanisms. It will be divided into two parts as well. The first one is how the pipeline really work. I mean, how the data flow in the pipeline. What kind of additional register we have to build in order to pipeline to work. Then the second part will be how to control the whole pipeline. A bit more complex, but let's start with the first part. For illustration, we use the same processor, okay, same data path, okay, which has now 5 pipeline stage, and we call instruction fetch, decode, execution, data memory, and write back. We have a dashed line to sort of divided our data path, the active area, into 5 areas according to 5 stages of pipeline. We want to emphasize this to blue line. When the pipeline work, it go as you can imagine, like a previous illustration, from left to right. So fetch, right, decode, execute, data memory, read and write to the memory, and write back to the register. All the data flow go from left to right, except these 2 blue line. Obviously, because this one will decide the next instruction if you have branch. Either you use the next instruction going from the result here, or you branch. When you branch, you take this result from calculating the effective address. Part of the instruction come from the current program counter, and another part come from small offset in the immediate small number in the instruction. Jump to location 40, for example, then you add 40 to program counter and use that as your destination if you want to jump. Right? Otherwise, it's just using next instruction, which is program counter plus 4, because each instruction is 32-bit. And this is one that the data go right to left rather than left to right. The next one is obvious because you want to write back, right? So the output, whether it's come from ALU or reading the data from the memory, we need to be written to the register, right? So it go back here to the register. All right. Using the data path, it cannot execute 5 instructions simultaneously yet. If you have one register, say let's say register 5, right? You have two kind of activity. Is the most important is it is being used by you can write the data into the register, okay, and you can read the data from the register. Reading is no problem, right? You can read the register all the time, but you cannot write. You can write into the register only one at a time. Okay, so painting is a kind of gray area in this picture. Right? Say let's register. Gray area is when register. I think this picture show it divided into 2 phases. The first, if we want to, we write the register in the beginning and then read it afterward. Okay, rather than read it and write, we write it first. If we want to write it, otherwise we just read. Okay, that the result may be from the reading the memory, okay, or the ALU is written in the register here. One activity we divided it, write in the beginning and then read afterward. So this is how we divide everything into half here. ALU have no memory, so we don't have to think about it. It just has been used 100% all the time. Output depend only on the input. Okay. Unlike the register. Okay. When you present the data to, when you read the register, you just read it out. The content will change only when you send the signal, say that, hey, write into this register with the new data. Otherwise, if you do not written, no matter how you change the input of register, output will not change. It change only after you send right signal to it. Okay, so you can control when to change. This is show if you say execute 3 instruction in this sequence, if you go like this, okay, you can see the detail what happened when. Okay, but it goes just normal pipeline. Okay, for the so you can imagine that there's a kind of big bank of register here. Okay, separating 5 stages of data path. Okay, now we will consider what should be done to run the pipeline. Now, because we draw this diagram in such a way that we can divide that clearly, and we now insert a kind of big register. We don't know. We will analyze how many bits are there in each stage. Okay, so a kind of connecting. That's the similar one. Connecting the left to the right. But now this stage we have the memory. Okay, so on the left it can do something. On the right it can do different things. Okay, even previously we are on the same wire, right? Now we separate the wire and have the memory here. So this stage will change only when we write the new information to this kind of pipeline register. Okay, so this is additional hardware you have to put in to make the pipeline work. Okay, so this slim box we also have 2 parts, right? You have to write it before the output is changed. Okay, otherwise whatever change here will not affect the next stage. Only when you write the new data into this pipeline register, then the output will change. Okay, so to begin with, we just cut it like this and put in a lot of register. Okay, to connect to not to disconnect. Okay, to disconnect between the left side and the right side. So now it's really an independent 5 stage. Okay, instruction memory hold 1 instruction, right? Not hold many instructions, but it read from instruction memory 1 instruction at a time. So 1 instruction is 32 bit. So at least this Y is already 32 bit. Now the next Y here is a program counter. This processor is 64 bit. So this Y must have a 64 bit. So totally this instruction fetch register, instruction fetch pipeline, or called IF/ID. Instruction is it between fetch and decode. So let's say fetch decode pipeline register must have 64 bit plus 32 bit, so 96. And you can similarly reason about how many Y. Okay, so this one is also because arithmetic logic unit is 64 bit, so it's 64 here and also 64 here, so 128, right? Just these 2 connection, and this one is also 64. So execution to the memory, this register is very big, right? So there's so many Y connected here. Right? All right, so now you can see that the different pipeline register have different size depend on how many Y we want to disconnect on this stage on two sides. I will explain now how to execute each instruction go through stage in the pipeline. We have a 5 stage, so we go one by one. Right? Instruction fetch. You read the instruction from the memory and you write that instruction into this pipeline register. Instruction memory is being used or is it read already. The next instruction is ready here because program counter is read and adder is also +4 ready to be used here, but not yet all the Y on the left hand is update their data into this register. So this is instruction fetch stage. You can imagine the next phase will be going to this area. The second half, the next clock, so to speak, we read information from the pipeline register because all this Y already have some valid value for the instruction that we are executing. I think this is a load instruction. Okay, so there's nothing happen here. Actually, there's nothing at all happen in doing the register file because the load instruction will be activated on the, I think, the data memory. Okay, so they're doing nothing here, right? But however, in general, the register is read, okay, and then all this Y value, including the immediate value, it partially come from instruction, right? So it come from this wire here, and the data is updated to the ID/EX pipeline register here. Okay, so the next clock, this pipeline register is valid for this instruction. For this instruction will be execute. Okay. Next, the same instruction now come to the third stage. Okay, so third stage, for the load instruction, the execution is just to calculate the effective address, right? For the value, part of the value come from register plus some small constant to be effective address. Register value is already read from the previous stage, right? And the value update to the Y in the ID/EX stage. So the value is already valid here to be added by ALU, and the result become effective address or the output from the ALU here, and is written into EX/mem stage. Okay, so this one is now valid. I mean, all the value on the Y is correct for executing the load instruction. So we have effective address, right? We have the control signal, which is not used now, not control the data to be written because it is load, not store. So we read the data memory. Okay, we presented the address, and then the data come out, and we update the information to the mem/writeback register, pipeline register here. So now all this Y will be valid to be used. Okay, for return this data back to the register. So the last stage, we just write back. We go to this value here, pass through the multiplexer by a proper selection of which one. In this case, we just use the top one. It's by selecting the port 1, we go to this, right? And then update the register. This is one instruction. But if we have many instructions, then we have to we have to arrange it so that there's no conflict. You can see that you have to be careful because at this moment, if there are other instructions in the pipeline, then that instruction will be also use the decode stage as well. So you have to avoid what we call clashing. Right? One want to update the register, another one want to read. You have to make sure that you are reading the correct one. So this is how one instruction goes through all the 5 stages. Now, that is a load instruction. If we change that instruction into store, we are not going to repeat the first 2 stages. Right? For the store instruction, when it executes, similarly, it's similar to load. It's calculate the effective address. So use one constant number and one address from the value of the register, and then add them together to become effective address. Right? And next stage is to access the memory. Okay. And to access the memory now, this is different from the load because now you write the data into the data memory. Okay. So you present it with the address, which we just calculate the effective address, and then present it with the data, and then send the control signal, write it. So the data memory is written. Okay. And there's no write back because no need. We store the value of register to the memory. No need to write anything back. Okay. So write back does nothing. Okay. We must have some additional wire down here to pass the address. You want to write back not the address, the value of the register. If you say you want to load x1, the value, the number x1 have to be present, right? Because it has to be reused when it go to the write back stage. So it cannot just disappear. So you have to have additional x1 value, so to speak, go through all the stage into the write back. So you have the value x1 here as well. The write back, the data flow back in time, right? So to speak, right? So you need some information. So the value that you just read from the memory can be stored back to the correct register. All right. So we need an extra blue line. The data is already correct because the black line here come out from the multiplexer of the last stage. So the value is correct. Okay, so this is an extra one that we have to put in. Otherwise, it won't work, right? We can show you the pipeline that run many instructions at once. Now we know how one instruction go through 5 stages, okay, including extra Y and extra register to separate the stage. So the data part is complete now. Is ready to run the actual pipeline. Okay, so we now run 5 instructions at the same time. The load, subtract, add, load, and add. Okay, let's see what X10. Okay, there's no data dependency here. So load use the X10 and is not used everywhere. Right? So this make the illustration easier to understand. And subtract, okay, X2, X3 to X11. There's no data dependency anywhere in these sequences. So when all those 5 instructions go through the pipeline, the gray area is the portion of data path that being used. Okay, so when 5 instructions, because we need 5 instructions to fill in the 5-stage pipeline like, completely, right? So now all this gray area is, we have no branch instruction yet, right? So the one of the inactive area is calculating the next branch instruction to be taken. What you might need to pay attention to is that the vertical axis show the activity of one stage. Okay, when the difference between, because now we have 5 instructions in the pipeline. So when we look vertically, you can see that this is fetch instruction of this instruction, and this is decoding of this instruction, and this is execution of this instruction, and this memory of this instruction, and this is write back of this instruction. Okay, let's see vertically. All right, so this one fetch to the next. Okay, register not being interfere, right? My idea is for you to really look at this diagram, and you can imagine why the 5 instructions can go at the same time in this data path with additional pipeline register and some small information, right, for the load instruction to go back. For example, if you see the data memory action, right, for this instruction is it will be written. Okay, so for this instruction it does nothing because it's not concern load, so it's all white, non-active, right? And for add instruction also non-active. For load instruction, right, it is written into on the first part and have been used. Okay, so read on the second part, and also this is non-active. So you can even look at the one unit through time, right? You can see, oh yeah, at a different time, this unit execute or serve different instruction. Okay, from the previous picture we just saw, we can argue that the 5-stage pipeline, that not all instructions are active in every stage, right? Okay, this is an observation from previous picture. And I asked you to think about the truth of these four statements. Okay, let's say we ignore all the hazard. Okay, if we shortcut the branch instruction, right, it does not have go through the 5 stage, then performance will increase, because if we jump, then you don't have to use load the last 2 stage, right? When we execute, we already know the address to be jumped, so it's no need for data memory access and write back. Okay. This is the first statement. I will not review the solution. Okay, you should think about it yourself. Second is, does not help. Okay, because the throughput That means you have to execute 5 stages, right? It's if you shortcut some instruction, it just make latency, not the throughput. This is a statement. You have to determine is it true or not. All right. The third thing to consider is whether you can take fewer cycles. Okay. Oh, you cannot improve ALU anyway because you need to write back. Okay. And branch can, because there's no, as I said, no write back stage. Okay. So there's an opportunity for improvement. This is a third way of thinking. Okay. The fourth one is very, very valid. And there are examples of the actual CPU doing it this way. Right? It say, hey, rather than concentrate on individual instruction, because we know the improvement depend on the number of the stage of pipeline. Our CPU right now have 5 stages. Let's make them 10, then it go 10 times faster. So that instruction take more cycle, right? So the more latency. Rather than 5 clocks to finish, it now take 10 clocks to finish. However, processor can run 10 instructions at the same time. That finish the first part of how the pipeline really works.